Hi everybody, Physics Ninja here, and welcome to my review on electromagnetic waves. What we're going to do today is look at 6 problems. I got 25 questions relating to electric field, magnetic fields, calculating the frequency, the wave number, the wavelength, the direction of propagation. How do you evaluate the Poynting vector and the intensity of electromagnetic waves? Alright, so what I suggest you do is you go in the description and click the link to download the problem set. Work through some of the problems and then come back and watch the video. Now you have to work through some of the problems. If all you do is watch the video, you will have learned nothing. Alright, like with all my videos, if you like this one, give it a thumbs up. Consider subscribing to Physics Ninja. It's the best way to support what I do. Alright, let's get started. Alright, here's our first problem. It says the electric field for a plane electromagnetic wave in vacuum is given by this expression over here. What is the frequency of this wave? Alright, so what we're looking for here is the frequency f of this wave. Well, one thing we automatically know is we know the speed, and we know that is related to the wavelength and the frequency through this expression right here. Now, if you look at my expression for the electric field, they have also told us what this number is, okay? And this number right here is the wave number of this wave. So k is actually 0.7, and 1 over meters are the units for that. So one thing to remember is that this quantity k, this wave number, is related to the wavelength, right? So you know this is 2 pi divided by lambda. So one thing I would probably do right away is if I'm looking for frequency, I actually do know the wavelength, or I can calculate it using this simple expression. But I'm just going to eliminate wavelength now and to write it in terms of this wave number, which I know. That's 2 pi divided by k multiplied by f. Now, the only unknown in this expression right here is the frequency. So you just isolate. So f, then, I bring the k on the other side. I get ck over 2 pi. And now all we do is we substitute our numbers. So we get 3 times 10 to the 8 for the speed of light. And now we have our wave number, which is 0.7, and then divided by 2 pi. All right, you put the numbers in the calculator, and we should get a frequency that is roughly 3.34 times 10 to the 7 hertz. And that there corresponds to choice A is the correct answer for this problem. All right, what is the magnetic or the magnitude of the magnetic field oscillations? All right, so again, if you're given an expression like the one up above here, you should know that the amplitude of the electric field, you typically call it E0 or E max. That guy right there is 1300 measured in newtons per coulomb. Now we're looking for the amplitude of the field right here. So what we have to do is we're looking for B0. Now these are linked together, okay? And the expression that links them together is this one right here. C times B0, like this. So what you're looking for here is B0. All you have to do then is simply take that electric field and divide it by that speed of light in vacuum. So here we're going to have 1300, and here I'm going to have 3 times 10 to the 8 meters per second. You put those numbers in your calculator, you should get something like 4.3 times 10 to the minus 6. And those units come out to be in Tesla. So that means that A is the correct answer right here. All right, the next one is, in what direction does the wave propagate? All right, so this one you have to be a little bit careful. If I go ahead and I rewrite this expression right here, I'm going to write my field equals to that amplitude 1300 sine. Now look what they have. They have a negative sign here in front of that 0.7. Now multiplied by z plus omega t. And that field is only in the x direction. So one thing we should know right away is that the direction of propagation should be perpendicular to the electric field and the magnetic field. So it definitely cannot be choice A. But we are now left with 2 choices. And having this combination of signs is a little bit different. So this is what I would suggest we do. I would factor out a negative sign. So I would write minus up here. Let me open up a bracket. If I factor it out, I do 0.7z minus omega t. Close the square bracket, close the curved bracket. All right, so this is the exact same expression. Now what I would do is I would use some of the properties of the sine wave, right? The sine is an odd function. So if I have sine of a negative number over here in the square bracket, what do I end up doing? I could take the negative sign outside, minus 1300, sign, and now it just becomes 0.7z minus omega t, and that's in the x direction. So the direction of propagation now, it's much easier. Once you have it in this form right here, you should be able to indicate that the direction of the propagation should be in the positive z direction. Okay. All right, so that's it for problem 1. Let's go to the next one. Let's look at problem 2. We have a linearly polarized electromagnetic wave propagates in vacuum. The electric field associated with that wave is given by this expression. All right, the figure above shows a snapshot of the electric field at time equals to 0. Yeah, if you set time equals to 0 there, you have an electric field that simply varies like a sinusoidal wave. So it starts at 0 and then just does a nice friendly sine function. All right, here's the first question. It says at time equals to 0, which option best describes the relative amplitudes of the electric fields at points A, B, and C? Note that A, B, and C lie on the XY plane. Okay, so how would we look at the magnitude? Well, look at the magnitude at point A. I'm going to call that EA, right? Clearly that one right there looks to be right here. That's the amplitude at that point. That there would simply be E0 at that specific time. Another easy point is point B. Point B lies right here, right on the axis, right on the x-axis. And you can see that its amplitude is actually 0 at that point. All right, so what we have to do now is think about what is going on at point C. Now, point C is a little bit above, right? It has a y coordinate, number one. It has the same x coordinate as the point B. So, and let's think about my expression. This expression here, that total amplitude of the field, really only depends on the x coordinate of those points. And B and C have the exact same x coordinates. C simply has a y, but y doesn't come into the expression over here. So that means that both of those here have to have the exact same amplitude. All right, so put that all together, what do we get? EA has to be the maximum, and EC equals to EB, and we should have something like this. Choice C is the correct answer. All right, next problem says, which of the following best describes the magnetic field associated with the electromagnetic wave? All right, so one thing is worth noting is we should cancel out a couple of the choices right now, okay? We know that E must be perpendicular to B, okay? That is something we always have for these electromagnetic waves. The other thing is we know that, so we can cancel out here a bunch of choices. Anything that has B in the Y direction is not going to be perpendicular to it because, look at my electric field is in the Y direction. So I would get rid of that choice, I would get rid of that choice, and I would get rid of that choice. So I'm now left with two choices. Notice they're both in the Z direction. All right, now one of them is positive, one of them is negative, and other than that, they're the exact same terms. So how do we determine the direction? All right, so for this one, we have to go back to what is the direction of propagation of my starting wave right here, right? If you look at an expression like this, okay, we should know that just by looking at these arguments, when I have a positive sign here for the omega t, I should know that this wave here propagates along the negative x direction, okay? That is something you have to know. Okay, so if it propagates along the negative x direction, it really only gives us one possible choice for the B field. Now, I would remind you of something called the pointing vector. The pointing vector, we define it as S, and it's defined as something like this. It's just a constant term, but the key to the pointing vector is really this, E cross B. Okay? The pointing vector gives you the direction of propagation of the electromagnetic waves. Okay? So if I can find what is the direction of E cross B, I know the direction of the magnetic field. All right, so how do we do this? Well, let's try it out. Let's think about which direction of E cross B would give us a wave propagating in this negative x direction. Okay? If I put a B field here with a Z, positive Z component here at the beginning, and I do E cross B, I'm going to find positive x direction. And I know that can't be the case. So I really have to draw the wave like this. B has to be like this. So it'll start off by having a negative Z component. Try doing E cross B now for these two fields. What you're going to find at this position, for example, I have a maximum E field. I'm going to have a maximum B field that is along the negative Z direction. You do E cross B, you're going to get a wave that propagates in this direction. All right, so for that one, the correct answer has to be choice B. Circle that guy. All right, what do we got next? If the amplitude of the magnetic field is given by this expression, what is the average intensity of the wave? All right, so how do you calculate the intensity of an electromagnetic wave? Now, there are many ways to write down the intensity. The average intensity here is written as something like this. 1/2 epsilon 0 is the permittivity of free space. C is the speed of light. And I am simply going to write it here in terms of the amplitude. And it's the amplitude squared that matters if I write it only in terms of the electric field. Now, nowhere do I know what E0 is, but they do tell me what B0 is. And I know that I can link those magnitudes together by my expression. E0 is nothing than C multiplied by B0. So if I wanted to write the intensity expression in terms of the magnetic field, it should look like this. CB0, and then I square this term. All right, one other thing I'm going to do is remember that how do you define the speed of light? And maybe I'll just write speed of light squared. That can be written in terms of the permeability and the permittivity of free space. So let's work on this expression one more step. Here we have epsilon 0, here I have C. I am going to get a C squared here when I bring out this squared term. So that I'm simply going to replace that speed of light squared by mu 0, epsilon 0, and then I'm left with the amplitude of that magnetic field, and I have to square that term. Let's eliminate the permittivity of free space. And now at the end, I'm simply going to rewrite that intensity value as 1/2 C divided by the permeability of free space multiplied by that amplitude squared. Anyway, I'm just kind of doing a lot of algebra here just to write it in terms of quantities that are given here. There are many ways to solve this problem. Now you just substitute the numbers. I get 3 times 10 to the 8 meters per second. The permeability of free space, 4 pi times 10 to the minus 7. And now they've told me the amplitude of that magnetic field is 6 times 10 to the minus 5. Don't forget to square that term. All right, you put all those numbers in the calculator. You should get something like 4.3 times 10 to the 5. Now the units of the intensity work out to be in terms of watts per meter squared. All right, and that there looks like it corresponds to choice D. All right, let's go to the next problem. All right, here's problem 3. Microwaves in a home microwave oven can be modeled as a linearly polarized plane wave in a vacuum with a magnetic field given by this expression. Now the amplitude of that wave is 0.24 millitesla, and my omega, the angular frequency, is 1.8 times 10 to the 10 radians per second. All right, so what do we have now? Well, the first thing to do is calculate the wavelength. Okay, so how would I calculate the wavelength based on this expression? Again, I would probably start off with an expression that involves the wavelength, and how could I calculate that? I know the speed of light. Now, do I know the frequency? Well, I don't know the frequency, but I know the angular frequency. Now, those are related by this. Remember, the frequency and angular frequency are related by the 2 pi factor over here. So if I rewrite it like this, I simply now isolate for my wavelength. Let's go ahead and do that. So I'm going to get the wavelength is going to be equal to 2 pi multiplied by the speed of light divided by that angular frequency. Now you just substitute the numbers. 3 times 10 to the 8 for the speed of light. And now my omega is 1.8 times 10 to the 10 radians per second. All right, you go ahead and put all of those numbers in the calculator. You should get like 0.105. I've calculated that in meters. Now, if you look at all these choices, they're all written in centimeters right there, but clearly choice B has to be the correct answer. All right, here's the next question. The associated electric field is given by which expression? Well, what I would first suggest here is that I'm going to make a plot of what the magnetic field looks like. Now, the magnetic field here depends on the value y, so I'm going to set y over here. Which direction should I place x? Well, let's go ahead and just place it. I would just be a little bit careful here, because if I place x along this direction, you must also determine what is the z direction. And for this to be a right-handed coordinate system, I'm going to need that x cross y gives me z. So I actually have to have z that goes into the page over here to be consistent with a right-handed coordinate system. All right, so let's go ahead and plot what this magnetic field looks like. Okay, so it varies. First of all, it's in the x direction, right? So it should look like that. And if I plot it, for example, at time 0, all I'm doing is I'm plotting a sine wave along this axis. All right, so this is what the field looks like. Okay, so it's only along the x direction. That's given by this. And what else do we know? We know that the direction of propagation for a term that's given like this, where both of these, the wave number term and the angular frequency term are both positive, we know that this wave here travels in this direction at the speed of light. So that means that the vector E cross B must be in that negative y hat direction. You have to have that. So maybe we can cancel out some choices right now. It only gives us a couple properties or a couple options for the electric field in this case, right? The electric field certainly cannot be along the y direction. That there doesn't make sense. Get rid of both of those choices. It must be along the z direction. We also want them to propagate along the same direction. Look at this choice here. It has a negative sign. So we can't have that because this electric field here propagates to the right-hand side. So we can't have that. So they should be in phase, both of those terms. So we're left with a choice where we either have an electric field that is going to be positive at the beginning here, or it's going to be negative, right? Both of those choices are simply different from each other just by that negative sign. So now we got to go back and think about this cross product. Which direction would I place an electric field so that the E cross B gives me a vector that propagates along that negative y hat direction? Right? You should see right away that the electric field here should vary as something like this. Right? If I'm going to draw it, this here is the electric field amplitude at that specific point. Maybe call it E0. And you can see if I do the right-hand rule with both of those vectors, E cross B, I should have my thumb here pointing in this direction, and that is really what I want. So you see it has to be in the negative z direction, so that means that E is the best choice. Now notice here they have the amplitude written as B0C, and that just comes from our expression, right? How do you link those amplitudes? They're linked together by this expression. But that negative sign is going to be important over here. So choice E is the best answer. All right, next problem says, a round dinner plate of radius 10 centimeters is placed in the microwave oven in an orientation perpendicular to the direction of propagation as shown. Find the average power the plate can absorb. Assume the plate area is smaller than the wave itself and that the plate absorbs all of the energy impinging on it. All right, so how would I solve a problem like this? How is power related to all of these other quantities? All right, so one thing to remember is that the definition of intensity here is really my kind of average power divided by the area. So the intensity I could calculate based on all of these numbers because the intensity is related to the amplitude of the field and those other constants that were in the front. The area here relates to the area of this dinner plate, which I can easily calculate. So let's rearrange this equation here. That means that the average power here would simply be that intensity multiplied by the area. So how would I calculate the intensity? Still using that same expression. 1/2 epsilon 0 multiplied by c. And here I had the amplitude of the electric field squared. And that gets multiplied now by the area of that dinner plate, pi r squared. Now we might do the same thing that what we did in the previous problem. Since we're told what this amplitude of the magnetic field is, maybe I'm going to rewrite this expression here only in terms of the amplitude of the magnetic field. So let me do one more step before we substitute the numbers. So this is identical to what we did previously. What's going to happen here is one of those, the epsilon 0 will cancel once I substitute everything else in there, and I should have an expression that looks like this. I have c over mu 0, and this becomes the amplitude of the magnetic field squared multiplied by the area of that dinner plate, pi r squared. So I'm now in a position now to substitute in all the numbers. So let's go ahead and do that. So we got 1/2. I get 3 times 10 to the 8 for the speed of light. My permeability of free space is 4 pi times 10 to the minus 7. The amplitude of the magnetic field, now careful, it's given in millitesla, so 0.24 times 10 to the minus 3 Tesla, and I have to square that value. Now multiplied by pi r squared, the area of the plate, and the radius here was 10 centimeters, so that should be 0.1 meters, and I have to square that. All right, oh, this is not intensity. I'm so sorry about this. This here should be my power, our average power. Let me correct that right here. All right, so the average power here at the end, what do we get? And we put all those numbers in the calculator, and you should get something like this, 2.16 multiplied by 10 to the 5. And that there would be measured in watts, because the intensity is in watts per meter squared. So once you multiply by that area, you're going to get watts at the end of the day. And that there looks a lot like choice number C to me. All right, kind of a nice problem, okay? Just kind of dealing with different quantities here. But I think we got it. All right, let's go to the next one. All right, here we have the electric field of a linearly polarized electromagnetic wave is described by this expression here. All right, we have different quantities that we want to calculate over here. So let's go see how we can do this. So how would you define the amplitude of the wave? The amplitude of this wave is something I typically call E0 or E max. And in this case, it's simply the number in front of the sine or the cosine. In this case, it's simply 12 volts per meter. That is the amplitude of the wave. All right, how would I calculate the wavelength, for example? Well, they're not telling me what the value k is, the wave number here. However, I do know that the wavelength multiplied by the frequency has to be equal to the speed of light, which we know. And the number here that multiplies the time is always my angular frequency. And the angular frequency is related to the linear frequency by this expression 2 pi f. So let's go work on this. Here we have lambda, and instead of frequency, I'm going to replace that by omega divided by 2 pi. All right, now we simply have to isolate lambda. This is what you're going to get. You're going to get 2 pi multiplied by c and divided by omega. Now we substitute in all the numbers. 2 pi, 3 times 10 to the 8, and divided by the angular frequency is 6 times 10 to the 9. All right, we go ahead and you substitute in all of the values, and you should get something to the order of 0.314 meters. Okay, that is the wavelength. The frequency, well, that's very, very easy to calculate. My frequency is simply the omega divided by 2 pi. 6 times 10 to the 9 divided by 2 pi. Put those numbers in the calculator, and we should get something to the order of 9.5 times 10 to the 8 hertz. All right, the problem 4 says the direction of propagation of this wave. All right, now wherever you have something like this, where I have a positive for the wave number term, okay, and I have minus an omega t term, even if there is this extra phase factor right here, this is going to be a wave that propagates along the positive x direction, okay? That's something we have to know how to figure out. All right, so that's an easy one. Number 5 says the associated magnetic field with this. So how would I write the magnetic field? Again, I always like to draw a coordinate system just to think about the different field values. So here it's going to vary along the x. I'm going to do something like this. And I'm going to plot y over here and z in this direction right here. Now remember that we have the relationship that E cross B has to give us something along the propagation direction, which in this case is along the x direction. So this is going to help me draw out or think about what is the direction of the magnetic field. First of all, it must also be perpendicular to the electric field, right? So it cannot be along the y direction. It must be either along the positive z or along the negative z direction. So this is how I would write out the field. So I would write out the magnetic field is going to have some amplitude B0. Now, what else? Multiplied by cos. All of these terms are still going to be the same. Minus omega t. I'll just write it as omega t. And here I do have some phase factor, and that's okay. All right, so now we got to think about this direction. Is it going to be minus z direction or positive z direction? Again, if you think about this expression here, my electric field varies along the y direction. The electric field looks like this. That is E. So if you think about what is a vector, E cross B gives me a positive X direction. What you would have to do here is you would have to draw a magnetic field that looks like this. Okay, so this magnetic field here, this is what it should look like. It should be along this XZ plane. Everything should be in the XZ plane, right? Because if I do E cross B, I will get the right direction of propagation if I do that. So at the end, I should have a positive Z hat over here. Now, if you wanted to also solve what is the amplitude of this magnetic field, or the amplitude of the magnetic field, if you know the amplitude of the electric field, you simply divide by the speed of light. In this case, it would be 12 divided by 3 times 10 to the 8 meters per second. That would give me something small in Tesla, 4 times 10 to the negative 8 Tesla. All right, so we've defined all of the terms here. That's it, we're done with this one. All right, then question 6 says, what is the average pointing vector? Well, the average pointing vector, again, the definition of the average pointing vector is the intensity. Okay, so someone asks you the average pointing vector or the intensity, they're the exact same thing. And the expression for that is 1/2 epsilon 0 c multiplied by that electric field amplitude squared. We just substitute in all our values, so you get 1/2 permittivity of free space 8.85, 10 to the minus 12, speed of light 3 times 10 to the 8, and now my electric field, I just get it from over here, that's 12 squared. We put in all the numbers, and you get something like 0.19. That is measured in watts per meter squared. All right, so there's kind of a nice, kind of typical electric field problem that you might find on a test. Let's go to the next one now. All right, problem 5 says the magnetic field of a linearly polarized electromagnetic wave is described by this expression. The amplitude of that wave is 6 times 10 to the minus 10 Tesla, and our wave number is 3.14 times 10 to the negative 2, 1 over meters. Let's find all of these quantities that characterize this wave. The amplitude of the wave, again, that's simply our number. That's simply B0. That's the definition of it, okay? Now, if you wanted to, you can also find what is the corresponding amplitude of the electric field, okay? Because I know that the electric field, or the amplitude of it, is related by this expression. All right, so here we would do 3 times 10 to the 8, the speed of light, multiplied 6 times 10 to the minus 10. Tesla, I'll put those numbers in the calculator, we should get something to the order of 0.18 volts per meter. That's the magnitude of the electric field. All right, how do I find the wavelength? Well, the wavelength is related to this wave number right here. The wavelength is simply 2 pi divided by the wave number k. In this case, it's 2 pi divided by, this is 3.14 times 10 to the minus 2. Okay, that should give me a wavelength of roughly 200 meters. All right, next question says, what is the frequency? Well, the frequency we can calculate by noting that the speed of light is the wavelength times the frequency. Therefore, the frequency, speed of light divided by lambda, 3 times 10 to the 8 over my 200 meters, and I get a frequency that is 1.5 times 10 to the 6 hertz. Excellent. All right, question 4 says, what is the direction of propagation of the wave? So now we look at this term. We know that it has to propagate in either the positive z or the negative z direction. To know which direction, I must also look at this term right here. In question 4, I should automatically be able to write that this wave here propagates along the negative z direction. Let's just write that down. All right, problem 5 says, let's write the associated electric field. So for this, what I'm going to do is, well, we're going to note, let's maybe draw out what the magnetic field looks like, or at least draw out a coordinate system here. So since it's propagating along the z, I'm going to put my z-axis over here. This magnetic field is along the j hat direction. So let's put y direction to be up. Now, if you want a right-handed coordinate system, you better have your x direction that goes into the page. All right, so my B vector right here, let's just draw it in a different color. It should look like this. At time 0, for example, it is in the YZ plane, and it looks like this. And it propagates, here we know it propagates in the negative Z direction. So that there is the amplitude B0. So how now do I plot an electric field if I want the direction of propagation to be in the negative Z direction? Again, for this, I'm looking for this term, this E cross B term. That tells me the direction of propagation. This must be in the negative Z hat direction. So I have two choices. Either I place the field along the E direction, along the X direction. If I do that and I do E cross B, I'm going to find positive Z direction. So I really need my field here to be along the negative X direction right here. And if I do that, all the directions are going to work out perfectly. So this here is going to be some amplitude E0 that I calculated up above. And now you see if you do E cross B, you will find a wave that propagates in that negative Z direction. So how do I now write that as a mathematical expression? Well, I would write my electric field. Again, has some amplitude. Now I'm going to put the negative sign in right away just to keep that. All of these other terms here, the cosine, these are all the same because the waves are in phase with each other, plus omega t. And here all I have to do is put x direction. So I really have the negative x direction here by this negative sign all the way in the front. All right, question 6, similar to the previous problem, what is the average Poynting vector? By definition, the average Poynting vector is nothing more than the intensity of that wave, and that we can calculate as 1/2 epsilon 0 c multiplied by the amplitude of that wave squared. Put in all the numbers. I'm getting good at this now. I've memorized these. I've done so many of these problems that everything is stored in memory. The amplitude of the electric field, we had it up here. We calculated that. Let me just go ahead and use that value, 0.18, and I have to square that value. I put in all those numbers, and I think I get something like 4.3 times 10 to the minus 5 watts per meter squared. All right, that's it for this problem. Let's go to the last one now. And here's problem 6. One note, this problem deals with circularly polarized electromagnetic waves, okay? And we'll see what that means in a minute, but yeah, if your class doesn't require you to know anything about electromagnetic waves, you may want to skip this problem, or you can look at it just for just some extra learning. So here's problem 6. It says the electric field of an electromagnetic wave is traveling through vacuum is given by this expression. All right, now the first thing we notice is there's an X component and a Y component, right? And they have, look at different terms over here. We have a cosine and a sine. So that's what makes this a little bit different. They've also told us here that the wavelength is 0.5 centimeters, right? Before, when we had linearly polarized electric field, we only had one of those terms. So it was a little bit easier. But now what we have is something at an angle, okay? And it's constantly changing. So let's go ahead now and think about this. All right, first question says, what is the angular frequency omega of this wave? All right, well, they're asking us for omega, but they've given us the wavelength right here, 0.5 centimeters. So right away, I should be able to do some work. Again, I have C that's equal to lambda F. And let me get rid of the linear frequency, write it in terms of the angular frequency. So it's simply omega over 2 pi. All right, now all we have to do is simply isolate for the omega. So that means that omega is going to be equal to 2 pi multiplied by c divided by that wavelength. Go ahead and substitute the numbers. 3 times 10 to the 8 for the speed of light. And my wavelength now, be a little bit careful, that's 0.5 centimeters. All right, so we have to 0.5 times 10 to the minus 2. And that gives me a angular frequency of roughly 3.77 times 10 to the 11th, and that should be in radians per second. All right, this electromagnetic wave now, it's either unpolarized, linearly polarized, or circularly polarized. Well, it's certainly not unpolarized, right? Because that should have just all possible orientations, right? And here we have clearly a vector that has an X and a Y component. So we're down to it. Is it linearly polarized or circularly polarized? Well, it looks different from what we've been doing previously with linearly polarized. But let's try to explain why it would be circularly polarized. So let me go ahead and draw, for example, just an XY. coordinate system like this. And if I take times 0, so imagine here I take times 0, so I get rid of that term. So what are we going to have? We're going to have an x component of this electric field that looks like what? Let me go ahead and draw it. It's going to look like this. This is going to be the x component, okay? It's going to have a magnitude E0 divided by root 2 multiplied by cos of this angle. The y component now is going to look like this, okay? Sine of. So that might be something like this. This would be the y component, okay? First of all, the amplitude of both of those terms has to be the same thing, right? This is the x component and this is the y component. Notice that these are changing now as I go to different z directions, right? For example, when I'm at some corresponding angle here that corresponds to 45, they would be the exact same, right? And the total electric field here would simply look like something like this. But as you move down either into the plane or out of the plane, you're going to see that this amplitude is going to change, right? These x and y components are going to change. But the total vector is never going to change its magnitude. How would you calculate the magnitude of this vector? You have to simply square both components, add them together, and you're always going to find a constant magnitude. But what you're finding here is that sometimes that component is along the x direction, sometimes it's along the y direction. So this vector here actually rotates. It's going to rotate it in one of the two directions here, depending on the signs that you have for these corresponding terms. So that there actually corresponds to something called circularly polarized light, okay? This vector here will rotate around in this xy plane as I move in and out of the z coordinate here. All right, so that one is a little trickier than what we've done for linearly polarized light, but that is the argument. All right, what's next? Which equation best describes the magnetic field for this wave? Well, for this one we should be able to do because we still know what is the direction of propagation of the wave. The direction of propagation of the wave, if you look at either this term or this term, we should be able to say that this wave here propagates in the minus z hat direction, okay? That has to be the direction of propagation of the wave. All right, so that automatically tells us that E cross B direction has to be in that negative z direction. The other thing that I require for electromagnetic waves, regardless if they're linear or circular, is that the scalar product between both of those vectors has to be 0. So they have to be perpendicular to each other at all times. So I'm going to use that now to eliminate at least two of these choices. I'm going to eliminate this choice and this choice. You can see here you're going to have cos, and you have the same factor here, cos. Okay, so these are actually going to be, look at their cos terms are always the same. Also this one, this is a sine in the y direction or the negative y direction. This is also a sine. If you evaluate this scalar product right here between both of those, you're going to get a cos squared minus a sine squared, right? But we require this to be 0 at all times. That is not always going to be 0. The same can be said down here for this term. This is the exact same, except I've swapped this sign. If I evaluate this scalar product here, it's never going to be, or it might be 0 at one instant in time, but this requires that the fields are perpendicular to each other at every moment in time. So it cannot be any of those choices. All right, so what are we left with now? Well, we're left with 3 of those choices. So now we really have to think about this a little bit more. All right, so what I'm going to do now is let's go ahead and let's just take a look at the electric field and take a look at some moment in time. Okay, if you take that times 0 again, let's get rid of those terms. That'll make our analysis easier. And let's take a position, for example, at z equals to 0. When z equals to 0, I'm only left with a electric field that is along this x direction. All right, so let me draw my coordinate system again. I have x, y, and I'm going to have positive z that's coming out of the page. All right, so at this moment in time, and at time 0, and at position, all I have now is an electric field that looks like this, and the amplitude of that field is E0 divided by square root of 2 at that position. All right, so what must the direction of the magnetic field be at that specific moment in time? right? We know that the direction of propagation is the minus z direction. So at that moment in time, I better have a magnetic field that goes down like this, right? And the magnitude of the magnetic field is going to be B0. Again, you can calculate that as C E0 divided by square root of 2. That has to be the magnitude. You see, if you do E cross B, you're going to get a vector that propagates in that negative z direction, which is what we require. Okay, so right there, we might be able to eliminate one of the choices. We have that magnetic field must be, oh, look at this one. The first expression, A, would not give that because look, I have sign for both terms. If I'm evaluating this at time 0 and at z equals to 0, I get 0 for that magnetic field, and that's not what we have to have. So I'm left with two choices right here, and right away you could see we could eliminate choice B because choice B is not in the right direction. So without even doing any further analysis, I should be able to figure out that choice C has to be the best answer. What I would then do for the other one is I would look for a moment or a position in space Z where the second term is equal to its maximum value, and that'll mean that the cosine term or the x component of that field is going to be 0. And anyway, you'll convince yourself even further that choice C here has to be the correct answer. All right, and the last question for this problem set looks like this. Which of the following statements about the magnitude of the pointing vector for this wave is correct? They say it varies as a function of t, but is independent of z. S varies as a function of both z and t, or is independent of z and t. Well, what I would suggest for this is we're simply going to evaluate it. So I would write S, the definition of it is 1 divided by mu 0, and I'm looking for this cross product right here, E cross B. I've known what the total vector is right here. That is my electric field vector. And from the previous one, I know what the magnetic field vector is. It has an x and a y component. What you simply do is you find what does this cross product give you. So let's go, and I'm going to give myself a bit more space, go on the next page, and figure what this is. All right, so what we're going to do here is just start off by writing that pointing vector. And now let's do the E cross B. So what I'm going to do is I'm going to write down the electric field vector E0 root 2. And here we have an x component, cos. I'm not going to write down all the term over here because it just repeats itself over and over again, but let's just write it down like this, plus sine of the same term and in the y-hat direction. All right, now I want to do a cross product with my magnetic field right down here. So again, this here has a different amplitude, has an extra factor of c here in the denominator, but this vector also has an x component. This is sine, again, x hat, and then minus cosine, y hat. All right, whenever I evaluate a cross product, I always do a small coordinate system here just to help me out. Okay, so I think we're in a position to evaluate this pointing vector. Let's bring all the constant terms to the front so we get 1 over mu 0. The root 2's combine here to give me a factor of 2. What else? I get the amplitude of the electric field that gets squared, and I still have a factor of c here down here in the denominator. All right, so far so good. What else do we get? I think that's okay. All right, so now we have to FOIL this expression right here. So look at the first term. We don't have to worry about anything with x cross x. Those terms are going to give you 0. Also, the y cross y terms that you get over here, those also give you 0. The only thing we're left to worry about are all of the cross terms. Okay, so the first cross terms we're going to have is, let's just get rid of this here. All right, so we have the first term from the electric field and then the last term from the magnetic field. Notice that both of those are cosine terms. So you're going to get cosine squared of this entire term, and then you're left with the direction x cross y. X cross y gives you something here in the z hat direction, but don't forget about this negative sign here, so I'm going to put that over here. Okay. The other term that we have to worry about is this guy. So that's in the y direction for the electric field and the x direction for the magnetic field. Again, if you do that y cross x, that also gives you something in the negative z direction. And notice it's going to be two sine terms that we multiply, so it's a sine squared term of this entire angle. All right, we are now at the final expression. So we get E0 squared 2 mu 0 c. I'll bring the negative sign in the front. And look what we have here. We have cosine squared of this entire argument plus sine squared of that entire argument multiplied by z hat. Well, this should look like a very kind of well-known identity that there is actually equal to 1. Okay, so my pointing vector for circularly polarized light here, mu 0 c multiplied by the z hat direction. We see that this vector here is not only independent of z, but it's also independent of time. So right here is that the magnitude of this pointing vector here, the magnitude, you just drop the negative sign, but you can see that C is going to be the correct answer. All right, that concludes this problem set. Thanks for watching, folks. Good luck on your exams. We'll see you next time.